Hello everyone, I'm Wen Jingdong, a master student from Xianjiaotong University. It is a great honor here to share our research on optimal operation of hydrogen energy system considering electric power and vehicle-based hydrogen delivery. Nowadays, hydrogen has been an ideal companion for the stochastic renewable power. It is sustainable and can be produced by water electrolysis by the renewable power. It also features a clean consumption and serves the load with zero carbon emission. But how to send the produced hydrogen to the scattered load centers? Fortunately, hydrogen is easy for storage and can be delivered by many approaches, such as pipes, liquid tanks, and tube trailers. Among these, the tube trailer is the most cost-effective and well-developed method. The tube trailer moves on the roads and makes the whole system a coupled electric power and transportation network. So, many works have been devoted to the integrated power and hydrogen system, but they are limited to the component level. They lack the system-level research, in which hydrogen transportation plays an important role. So, it is of great importance to explore the synergy between the electric power and transportation networks in the hydrogen energy system. The hydrogen energy system is composed of three parts: hydrogen production, transportation, and load centers. Hydrogen can be produced by water electrolysis in the generation stations as a special kind of power load. The produced hydrogen can be loaded onto the trailers or put into storage. The hydrogen balance should be satisfied. The loaded hydrogen can be delivered to the load centers across the transportation network. The departure time and path selection can be optimized to minimize the transportation cost. It is actually a vehicle routing problem. So, the outflow constraints should be satisfied, which means each trailer can only be assigned one route for delivery. It is worth noting that if a trailer enters a station, it must leave to guarantee the delivery trip comes to be a closed loop. In addition, the auxiliary potential variable alpha is introduced here to eliminate the subloops among the HLCs. Different from the conventional vehicle routing problem, the hydrogen balance as well as routing should be satisfied in our proposed model. For the operation of hydrogen load centers, hydrogen balance should be met with the hydrogen storage considered. It should be noticed that hydrogen production and consumption are usually modeled on hourly or 15 minutes resolution, but hydrogen transportation are usually modeled in continuous time framework triggered by the departure and arrival events of trailers. So, to bridge the gap between the time-based and event-based parts, we come up with the linearization technique. An ILP formulation is developed. For example, if a trailer set off at 7:15, the hydrogen loading should be completed at 7 o'clock. Similarly, if a trailer arrives at 7:45, the hydrogen discharge should be scheduled at 8 o'clock. So, the system-level model of integrated power and hydrogen system is obtained to minimize the total cost, including electricity generation cost, renewable power spillage or load shedding punishment, and transportation cost. It is complex and difficult to solve directly, but fortunately, the problem is separable. It is composed of the following parts: electric power, hydrogen production, transportation, and load centers. They are connected by some simple hydrogen balance constraints. The ADMM-based method is used here. The coupling constraints between hydrogen production and transportation are relaxed, and these two sub-problems can be obtained. The one is the electric power system, and the other is the hydrogen delivery system. These two parts can be coordinated by the updating of the multipliers, and finally approximates the optimum of the primal problem. It takes 6 iterations to get a solution, although the time consumption is still large, but it is much smaller than the centralized optimization, which takes as long as 96 hours. For the case studies, these 3 cases are considered for comparison to show the effect of integrated operation of EPS and HDS. The coordination cost is reduced significantly compared with the cases where HDS or EPS is optimized first and then the other part. In addition, the transmission congestion is also alleviated as shown in the bottom right figure. It may be because the coordination provides a trade-off between optimal electric power system operation and least cost hydrogen delivery. Secondly, the hydrogen storage capacity at production and consumption side are considered. The cases with the higher HGS storage feature the less cost. It may be because electricity generation cost can be reduced by exploiting the hydrogen production demand response. The total cost also decreases with the increase of HLC storage. It is due to the fact that the HLC storage can level off the hydrogen load variations. Thirdly, the total cost also falls down with the increase of HGS hydrogen production level. It indicates that with the peaks of hydrogen production load and grid electric load staggered along the time axis, the total load is leveled off with the maximum reduced. In conclusion, this paper proposes an integrated power and hydrogen system with the transportation network considered. The time-based and event-based parts are properly connected by the MILP formulation. The model is efficiently solved by the ADMM-based method, and the total cost is reduced. Energy storage such as batteries and hydrogen would play an important role in the renewable-dominated power system. Such storage can be delivered by vehicles, inducing the coupled electric power and transportation network. In the future, we will study the optimization of system configuration with extreme event and stochastic travel congestion. Okay. Thank you for your attention. If you are interested, welcome to contact us.